Thank you, and good morning. I'm Jared Johnson, and I'm the design team lead for Northern Elements. Today, we'll be discussing the final design and performance of the NE1 Frontier. For the duration of this presentation, the screen above me will be referred to as the primary screen, and the screen to my side will be referred to as the secondary screen. This is the NE1 Frontier. The NE1A Frontier is shown on the primary screen. It was the initial configuration used in the initial wind tunnel model testing. The NE1B is shown on the secondary screen and includes the selected configurations after the initial wind tunnel model test. There are a few notable features of the Frontier, including the use of its larger tires and oleopneumatic struts in combination with its flying boat hull design to provide unmatched versatility in both land and water operations. The high wing design, coupled with the high-mounted engines, provides adequate prop tip clearance in rugged terrain and water. The airfoil-shaped mass underneath the high wing is a sponson and creates lateral stability in water, in addition to housing the larger landing gear. As you can see, the windshield is partitioned in the middle and the windows are rounded as a result of the Frontier being a pressurized aircraft. The larger empennage is characteristic of amphibious aircraft and helps counter the nose-down pitching moment created by the high-mounted engines. I would now like to take a moment to introduce the team responsible for the design of the NE1 Frontier. Chad Burge, Alexander Vladika, Mark Van Bergen, Jayant Bangalore, Nicholas Kearney, and Sergio Perez, and Blake Bradford. On the secondary screen, you can see an overview for the presentation, beginning with the motivation behind the design of the Frontier and leading into the initial and final wind tunnel tests and performance analysis, the structural analysis, and finishing with conclusions and recommendations. Chad Burge will now discuss the motivation for the Frontier.
Thank you, Jared. My name is Chad Burge, and I will now discuss the motivation behind the design of Northern Elements' NE1 Frontier. There are 201 communities in Alaska without direct access to medical facilities or regular resupply routes. 25 of these communities do not even have access to runways. This accounts for approximately 10% of Alaska's population. The remainder of the state must rely heavily on their infrastructure. The map on the primary screen shows that Alaska's 11 state roads are found almost exclusively on the eastern side of the state. Less than 5% of these roads were deemed in very good condition by the Bureau of Transportation Statistics. The remainder of these roads have been deteriorated by year-round icing or flooding. The secondary screen shows the expected takeoff and landing conditions the Frontier will be exposed to in these rural environments. The Frontier will utilize its large tires and oleopneumatic struts to help it to land on unimproved surfaces, its reverse thrusting capabilities to help it to stop on an iced over runway, and its flying boat hull design to enable it to land on the water. These unique takeoff and landing capabilities separate the Frontier from its competitors in the mid-size utility aircraft class. The primary screen shows a survey conducted in 2010 among seaplane operators. This survey showed that 42% of operators requested a seaplane capable of carrying 7 to 15 passengers. 29% of these operators requested a seaplane with a payload which is similar to the Frontier's. And 20% of these operators requested a range between 650 and 850 nautical miles. The Frontier is capable of filling this void in the market. The primary screen shows the Frontier compared against its three main competitors. There is no aircraft in production today that is capable of meeting the mission requirements of Northern Elements Frontier. For example, the Cessna 208B Grand Caravan must be equipped with floats in order to meet the takeoff and landing capabilities of the Frontier. This is a $50,000 installation in labor alone, not to mention that the aircraft can be grounded for up to 2 weeks. The Pilatus PC-6 Porter cannot carry the required amount of cargo nor the required amount of passengers, and the Antilles G-21 Super Goose is not capable of meeting a single mission requirement listed on the screen. The secondary screen shows the interior configurations of the Frontier for its three main missions. In order to be competitive in the marketplace, the Frontier must be able to quickly change configurations from 3,000 pounds of cargo to 2 litter patients with their accompanying medical personnel and equipment, and it must also be able to carry 12 passengers. The primary screen shows the Frontier taking off from both a hard surface as well as from the water. The Frontier is required to take off within 4,000 feet on a hard surface and from within 1 nautical mile on the water, clearing a 50-foot obstacle in both cases. The secondary screen shows the mission profile of the Frontier. The Frontier was engineered to take off from one of the surfaces mentioned, obtain a competitive climb rate up to its cruising altitude of 18,000 feet, where it may fly throughout the duration of its range of 800 nautical miles, at which point the pilots may begin their descent down to landing maneuvers. If at any point in this process the pilots deem the landing surface unsafe, they may perform a go-around maneuver and divert to a more suitable location to carry out the mission. The primary screen shows a 3-view of Northern Elements NE-1A Frontier. The NE-1A is the preliminary design that was engineered to meet these mission requirements. The 3-view shows that the Frontier is a mid-size utility aircraft with a wingspan of 61 feet. The secondary slide shows the whole design of Northern Elements Frontier. The stern post angle is 9 degrees, and it is the angle that the aft of the hull makes with the water. The step is located 17 feet aft of the nose, and this causes separation, which helps the Frontier break the suction when taking off from the water. And the dead rise angle is the angle the side of the hull makes with the water. This angle dictates how the Frontier gets on step, and it also dictates the splash angle upon landing. Alexander Vladika will now discuss the wind tunnel equipment and procedures.
Thank you, Chad. My name is Alexander Vladika, and I'll be discussing the wind tunnel test equipment and apparatus, as well as the procedures. If you look on the primary screen, you can see the ERAU-Lab 87 series wind tunnel. This is a closed circuit wind tunnel that has the dimensions of 32 by 45 inches wide and a max velocity of 235 feet per second. The angle of attack for this wind tunnel is adjusted automatically through a Velmex motor, and the side slip angle is adjusted manually just underneath the balance. On the primary screen, you can now see the wind tunnel model with the white tufts attached to it. This is used to help identify flow visualization characteristics such as stall and flow separation. Additionally, the tufts trip the boundary layer, which help closely approximate the flow of the actual aircraft. Modeling clay was used to help smooth the transition between assembly parts. On the secondary screen, you can see UV lights installed inside the test section. This is used to help enhance the contrast between the white tufts and the black model for flow visualization characteristics. Now I'll be discussing the wind tunnel test procedures. On the primary screen is one of the 2 tests that were performed to determine the wind tunnel velocity. The first test was a structural test. This was done by placing 12 1-pound sandbags symmetrically on the wing until a wingtip deflection of ½ inch was seen. More load was placed at the root core of the wing than the tip of the core of the wing. Using the 12-pound sandbags to approximate the maximum allowable lifting load, known model geometry, and maximum lift coefficient, a max velocity of 131 feet per second was determined. On the secondary screen was a second test that was performed. This was the aeroelastic test. This was done by increasing the model to its highest angle of attack of 26 degrees and increasing the wind tunnel velocity slowly until wingtip oscillation occurred. To avoid structural damage due to wingtip oscillation, the wind tunnel velocity was limited to just 85 feet per second. On the primary screen, you can see the 3 configurations that were tested inside the wind tunnel. The first was the full model, the second was without the empennage, and the last was a fuselage only. On the secondary screen, you can see an exploded view of the model assembly parts. You can notice that a clean cone was replaced for the without empennage and fuselage configuration only. On the primary screen are the longitudinal data that was collected. Angles of attack from -4 to 26 degrees were measured in just 2-degree increments. Data such as coefficient of lift, drag, and pitching moment was collected for this test. On the secondary screen, you can see the lateral directional test that was performed. This was performed from angles of 0 to -10 degrees in the same manner of just 2-degree increments. Coefficient of yaw and roll moment was collected for this test. Next, Mark Van Bergen will be discussing the initial wind tunnel model.
Thank you, Alexander. My name is Mark Van Bergen, and I'll be discussing the initial wind tunnel model for the NE1 Frontiers wind tunnel testing. On the primary screen above me, you can see a 3 view of the initial wind tunnel model. The initial wind tunnel model was based off the NE1A configuration. We scaled this from the initial design to a 1/32 scale using 5 main criteria. These 5 main criteria were the avoidance of wind tunnel blockage, the avoidance of wind tunnel wall effects, the trying to keep the model from overstressing the balance, which had a maximum limit of 40 pounds. We had to fit adequate structure within the model, and finally we had to keep all the printed components under our $500 budget. On the secondary screen you can see the CG locations in both the X and the Z direction for the full model. On the primary screen is an animation de-assembly process, starting off with the assembly of the tail. The tail utilizes steel support structure and was epoxied in place. The nose is then epoxied onto the main hull, and the sponson support structure and sponsons are inserted and glued in place. 2 wing support blocks are then inserted and held in place with 4 countersunk screws coming up from the bottom. The main hull and nose section are then slid onto the main support bar, and the stand is placed. This is secured with 2 countersunk screws from the top. The main fuselage is then attached, and the tail is attached to the rear spar cap. This is then attached to the back end of the model and is held in place with a machine screw that is tightened with an Allen key. 2 1/8-inch steel rods are then slid in through holes in the main fuselage, and the wings are attached with locating tabs. These are secured in place with 2 countersunk screws that are inserted from above. These 2 screws are the only fasteners that are exterior, and they are covered over with modeling clay during actual testing so as not to affect our results. On the secondary screen you can see a ghost view of the assembled model with the assembled structure clearly visible. I will now discuss the initial design verification and results of our initial round of wind tunnel testing. For the remainder of this section and for the rest of the presentation, the results from our preliminary design phase will be denoted with the predicted, and then the results of our initial wind tunnel test will be denoted with NE1A for all the charts. On the primary screen you can see the lift curve slope for both the preliminary design phase and the initial round of wind tunnel testing. You can see that our max CL was significantly decreased as a result of our wind tunnel testing, and the wing stalled at a 14-degree angle of attack. However, the stall behavior was determined to be extremely docile. On the secondary screen you can see flow visualization from above of our aircraft at 14 degrees angle of attack. This shows the stall, which is denoted by the displaced tufts on the trailing edge of the wing. On the primary screen you can see the drag versus velocity verification for both the preliminary design and for the initial round of wind tunnel testing. You can see we do have a much higher drag coming off the wind tunnel testing. One assumption that we made that caused this was the step, which was unaccounted for in the preliminary design phase. You can see the displacement of the separation due to the displacement of the tufts behind the step on the secondary screen. On the primary screen you can see our longitudinal stability verification. You can see that the initial round of wind tunnel testing allowed us to determine that we are neutrally stable at low angles of attack, and then at higher angles of attack we closely match the predicted values. On the secondary screen you can see that the lateral stability verification shows that we are quite a bit more unstable than was predicted. On the primary screen you can see the directional stability verification showing that our initial round of wind tunnel testing closely matched our predicted values. On the secondary screen you can see our static stability derivatives and their respective stability criteria. This shows that we are stable in pitch and yaw, but are unstable in roll. Now Janth Bangalore will cover the initial performance verification.
Thank you, Mark. My name is Janth Bangalore and I'll be going over the initial performance verification. On the primary screen is the power available and the power required plot for the sea level. The green line indicates the power available from the two turboprop engines. From this plot, the power required for the NE1A was higher than predicted. The difference between the power available and the power required is denoted by the maximum P sub S, which is the maximum specific excess power. At this altitude, the maximum excess power for NE1A is 1,270 feet per minute. And the maximum operating velocity, which is the intersection between the power available and the power required curve, is 175 knots. On the secondary screen is the power available and the power required for 6,000 feet. As the altitude increases, the power available shifts down and the power required shifts up to the right. At this altitude, the NE1A has a maximum P sub S of 1,270 feet. On the primary screen is the power available and the power required for 12,000 feet. As the altitude increases, the power available continues to shift down and the power required continues to shift up to the right. At this altitude, the power available for the NE1A is 610 feet per minute. On the secondary screen is the power available and the power required for 18,000 feet. At this altitude, the NE1A has a maximum P sub S of 0 feet per minute and a maximum operating velocity of 155 knots. On the primary screen is the predicted specific excess power plot for 0, 500, and 1,000 feet per minute. At this altitude, our absolute ceiling is 21,570 feet. On the secondary screen is the NE1A specific excess power plot. From this plot, the NE1A altitude absolute ceiling decreased to 18,000 feet. On the primary screen is the takeoff distance comparison. To be noted that the takeoff and the landing distance were calculated using the Brandt's equation, utilizing the lift, drag, thrust, and friction coefficient. On the primary screen is the highlighted value, which is the longest takeoff distance, which is from the water. This still meets our RFP requirement of 1 nautical mile. On the secondary screen is the landing distance comparison. The highlighted value shows the longest landing distance, which is from ice. The NE1A will utilize its reverse thrusting capabilities in order to meet its RFP requirement. On the primary screen is the predicted range for the 3 payload configurations. To be noted that the shape of the range projection is due to the Mercator projection. The longest range is achievable by the litter configuration of 1,032 nautical miles. On the secondary screen is the NE1A range for the 3 payload configurations. The range for the litter configuration decreased to 765 nautical miles. On the primary screen is the predicted flight envelope. The upper and lower bounds of the flight envelope are bounded by the G limits, dictated by the CFR requirements. The right bound is dictated by the Q limit, which is the maximum operating velocity at a particular altitude. The maneuvering point, which is shown on the screen, is the point at which the aircraft can perform its quickest and the tightest turn. On the secondary screen is the NE1A flight envelope with the maneuvering point indicated. Now I'll be going over the design modifications. On the primary screen is the design of the modified wing. From the initial wind tunnel results, it was determined that the frontier is unstable in roll. In order to improve this, a leading edge sweep of 5 degrees was added on the main wing. The secondary screen shows the swept wing attached to the wind tunnel model. On the primary screen is the winglet design. From the initial wind tunnel result, it was determined that the frontier has higher drag than predicted. In order to improve this, winglets were designed to increase the lift and decrease the drag. Blended winglets were designed with a cant angle of 30 degrees and a leading edge sweep of 33 degrees. On the secondary screen is the winglets attached to the wind tunnel model. On the primary screen is a design of a retractable step fairing. From the initial wind tunnel flow visualization data, it was determined that the step on the fuselage produces high drag. The step is one of the main contributors of the fuselage drag because of the flow separation. In order to reduce the flow separation, a step fairing was designed to be attached to the model. On the secondary screen is the design of a step fairing attached to the wind tunnel model. On the primary screen is the modified wind tunnel model with the swept wing, winglets, and the step fairing attached. On the secondary screen are the 4 different test configurations in which the second wind tunnel test was performed. This was done in order to analyze the individual contributions of the modifications and to analyze its performance improvements. Angle of attack test was done from -4 degrees to 26 degrees in 2-degree increments, and a beta test was done from 0 degrees to -10 degrees in 2-degree increments. Next, Nick Kearney will discuss the model modification analysis.
I'm Nick Kearney, and I'll be discussing the model modification analysis. The primary screen shows the pitch stability for the modified configurations of the Frontier. The addition of leading edge sweep to the model has improved the pitch stability characteristics of the model by shifting the location of the aerodynamic center aftward. The secondary screen shows the roll stability characteristics for the modified configurations. This plot also shows that the leading edge sweep improved the roll stability of the model. The primary screen now shows how the drag changes with velocity for the various modified configurations. From this plot, you can see that the winglets reduce the amount of induced drag on the model. The secondary screen now shows how the lift coefficient changes with angle of attack. From this plot, you can see that the configuration with the leading edge sweep and the added winglets produce the maximum lift coefficient. From the wind tunnel analysis, Northern Elements has decided to implement 2 of the modifications. The first modification Northern Elements has decided to implement is the addition of 5-degree leading edge sweep to the wing of the Frontier. The second modification Northern Elements has decided to implement is the addition of winglets to the wingtips of the Frontier. Northern Elements has decided not to implement the faired step modification as it had no significant impact on the wind tunnel test. The secondary screen shows the B model of the NE1 Frontier. The NE1B is the modified version of the NE1A. The NE1B includes the 5-degree leading edge sweep and has installed winglets. I will now go over the wind tunnel comparisons for the NE1A model, wind tunnel model of the Frontier, and the NE1B wind tunnel model of the Frontier. The primary screen shows how the lift coefficients varied with angle of attack for both models. From this plot, it was determined that the wind tunnel model for the NE1B began to stall at an angle of attack of 10 degrees. The secondary screen shows a flow visualization image of the NE1B at 10 degrees angle of attack. On this image, you can see that the tufts are indicating separated flow near the trailing edge of the wing. The primary screen now shows how the drag varies with velocity for the 2 model configurations. On this plot, you can see that the NE1B has reduced drag at lower velocities. The secondary screen now shows the pitch stability for the model configurations of the Frontier. The negative slope on this plot indicates that the Frontier is stable in pitch. The primary screen now shows the roll stability characteristics for the models of the Frontier. From this plot, you can see that the NE1B has improved roll stability characteristics at low side slip angles. The secondary screen shows the yaw stability characteristics for the models of the Frontier. The positive slope on this plot indicates that the NE1B is stable in yaw. Next, Sergio Perez will go over the performance comparison for the NE1A and the NE1B.
Thank you, Nick. My name is Sergio Perez, and I'll be going over the final performance comparison between the NE1A and the NE1B. On the primary screen is a power available and power required plot at sea level. The plot shows that the NE1B had a reduction in power required. This resulted in an increase in the excess power of 300 feet per minute. The maximum operating velocity of the NE1B is 165 knots. The secondary screen shows the power available, power required plot at 6,000 feet. Here, the increase amounted to 140 foot per minute climb rate to the NE1B. We also see that the power required continued to shift upwards and to the right as the altitude increased. Now the primary screen is a power available and power required plot at 12,000 feet, where we continue to see the shift in power required going upwards and to the right, while the power availability shifts downward, thus lowering our excess power. Here we amounted to an increase of 130 foot per minute climb to the NE1B. The secondary screen shows the power available and power required plot at 18,000 feet, which is the required service ceiling. Here we see the most drastic comparison between the initial model and the final model. Whereas the initial model had no excess power at this altitude, the final model had an excess of over 100 foot per minute climb rate, which is the minimum required for a service ceiling. The NE1A, on the primary screen is the NE1A specific excess power plot. The contoured lines show the range of excess power from 1,000 feet per minute down to 0 feet per minute, where the NE1A reached an absolute ceiling of 18,000 feet. The service ceiling was 17,310 feet. The secondary screen shows the NE1B specific excess power, where we had an increase in our absolute ceiling to 20,450 feet and the service ceiling of 19,350 feet, thus satisfying the minimum service ceiling requirement of 18,000 feet. Now on the primary screen is a takeoff distance comparison. The highlighted region shows the longest takeoff distance between the two models. It shows that our longest takeoff distance is in water. We see in this plot that even in our longest takeoff distance, we are still able to reach our RFP requirement of taking off within 1 nautical mile of water. The secondary screen shows the landing distance comparison between the two models. Here, the highlighted region shows that our longest landing distance is in ice. This is due to the low coefficient of friction and not applying brakes. Both models require the reverse thrusting capabilities of the engines in order to meet the RFP requirement. On the primary screen is the NE1A range for all three configurations. The maximum range for the initial model was 765 nautical miles. The secondary slide shows the NE1B range, where we show an increase in our maximum range of 845 nautical miles. Now on the primary screen is the NE1B flight envelope. Here, we notice that the maneuver point is located at 160 knots. We also see the Q limits at their associated altitudes. We have an upper G limit of 3.13 Gs and a lower limit of negative 1.3 Gs, as specified by the CFR requirements. I would now like to introduce Blake Bradford for structural design and analysis.
Thank you, Sergio. My name is Blake Bradford, and I'll be going over the structural design and analysis for the Frontier. On the primary screen are the different structural components that were designed. Spars run along the span-wise distance of the wing, and ribs run along the chord-wise distance. A cross-section of the spar is also shown. On the secondary screen are the purpose for each of these structural components, such as designing the spar caps to resist the bending moment incurred on the structure. Aluminum 7075 T6 was used for all structural components. Now this was chosen because of its higher strength-to-weight ratio when compared to other materials such as steel. The skin has an additional layer of stainless steel cladding in order to protect against corrosion for saltwater operations. The ultimate design load for all of the living body structures is 4.7 Gs. This came from multiplying a factor of safety of 1.5 times the maximum G loading of 3.13. Now this maximum G loading can be seen on the secondary screen's VN diagram. This VN diagram shows gust lines for 66, 50, and 25 feet per second. The maximum G loading came from the CFR requirement based on the weight of our aircraft. Now on the primary screen is the internal structure for the wing, along with the sizing for each of the structural components. The wing was designed to withstand the weight of the entire aircraft. The fuel tank is located in between the forward and aft spars. On the secondary screen is the wing's computational displacement analysis. Now all of the analysis will be done fixing the root cord to simulate a cantilever beam and applying 10-point loads across the span in order to simulate a distributed lift load. The maximum wingtip deflection here is 3.5 feet for a half span of 30 feet. Now on the primary screen is an idealized wing box analysis done at the root cord, because this is the most critical design for the wing. This was done prior to CAD modeling in order to verify the structural integrity of the initial structural design. The maximum bending stress was found in the lower left-hand spar cap, and this value is 53.6 KSI. The maximum shear was found in the forward spar's web, and this value is 15.5 KSI. Both the maximum bending stress and shear value is under aluminum's allowables. On the secondary screen is the wing's computational stress analysis. The maximum stress here was found at the root cord, and this value is 72.1 KSI and is under aluminum's allowable. Now on the primary screen is the internal structure for the empennage, where both the horizontal and vertical tails have the same component sizings. These component sizings can be seen on the secondary screen. The horizontal tail was designed to withstand the lift required for the front tier to trim at cruising condition. Now on the primary screen is the horizontal tail's computational displacement analysis. The loads applied on here were similar to that of the wing, where the root cord is fixed and 10-point loads are applied across the span in order to simulate a distributed wing lift load. The maximum tip deflection here is 0.47 feet for a half span of 13.75 foot half span. On the secondary screen is the horizontal tail's computational stress analysis, where the maximum stress was found at the root cord, and this value is 45.4 KSI. It is under aluminum's allowable. Now on the primary screen is the internal structure for the sponsons. Now the sponsons attach to the side of the fuselage and is the main support structure for our landing gear. On the secondary screen is a computational stress analysis for these sponsons. Now this was done fixing the root cord and applying a single point load to the location of the landing gear. Now the magnitude of this point load is half the weight of our aircraft times the dynamic loading factor. The maximum stress was found at the aft spar's root cord, and this value is 33.4 KSI and is under aluminum's allowable. Now on the primary screen is the overall internal structure for the front tier. This highlights the fuselage, wing, and empennage's structure and how all of these components attach together. On the secondary screen is the ghost view for the front tier, where it shows how the skin wraps around all of these internal structures. Up next is Jared Johnson, who will go over the market analysis.
I'm Jared Johnson, and I'll go over market analysis. The estimated cost for the Frontier was calculated using a cost per pound method between three similar aircraft. These aircraft manufacturers' costs were divided by their empty weights to obtain a cost per pound fraction. These fractions were then averaged and multiplied against the Frontier's empty weight to get an estimated cost per unit for the NE1 Frontier. This unit cost came to just over $3.2 million with an estimated operating cost of $800 per hour. This satisfies our RFP requirement of an affordable 50-unit purchase price. I will now go over labor and cost accounting. Our total projected hour trend line was calculated using the assumption that each team member would work 2 hours outside of class for each hour worked in class. This resulted in a total projected hours of 1,778, with the assumption that no hours were worked over spring break. Currently, Northern Elements is 38% over projected hours to date. On the secondary screen, you can see the hour breakdown for each category, most notably with administration taking 33% of our overall time to date. On the primary screen, you can now see the numerical value breakdown for our cost accumulation per category. Most notably, engineering has taken just over $32,000 of our budget, and professional development has taken just under $32,000. In total, Northern Elements has spent 2,466 hours on the project, totaling in just over $87,000 to date. On the secondary screen, you can see our breakdown of costs for each category, with professional development and engineering taking 36% and 37% of our total time, respectively. I will now go over conclusions and recommendations. The Frontier was designed to be a multi-surface amphibious aircraft capable of takeoff and landing on asphalt, gravel, ice, and water without the need to physically modify its landing gear. From the raw data analysis, Northern Elements identified the largest areas of improvement to be the roll stability and the increased drag from the predicted results in order to verify our preliminary results. From the model modifications, it was concluded that the implementation of the leading edge sweep and winglets increased both the performance and stability of the Frontier. The third modification of the step was not implemented, as this small increase in performance did not justify the added complexity to the model. From the structural analysis of the lifting bodies, it was concluded that the Frontier is stable and can meet all FAR Part 23 regulations. From the final performance comparison analysis, it was found that the implementations of the leading edge sweep and winglets increased the surface ceiling, range, and rate of climb from the initial model. Northern Elements would like to recommend that the flight test article include 5 degrees of leading edge sweep on the main wing. We would also like to recommend that the flight test article include the implementation of winglets on the main wing. And finally, Northern Elements recommends that the flight test article emulate the rendering shown on the secondary screen. This concludes our presentation. I will now field any questions.
Nice job, you guys. Excellent work. One thing that I got in this that I was tracking on, when I saw your wind tunnel data and your predicted drag at a certain value, and then your actual measured drag was much higher, which is not unusual for prelim to detail conversion. But the attribution was that the step was the cause of the drag delta. And then when you actually evaluated the step fairing to go and look at that effect, you didn't see that much of a result or that much of an impact with that fairing in place. Do you think that there may have been something else that was missing in your drag calculations in prelim, or was it just that the fairing wasn't as effective as you thought?
That's an excellent question. Chad Burge will actually answer this question for us.
So during the analysis, there was research that supported that the step could be responsible for up to 10% of the drag due to the hole. And so that was data that was quantifiable, and we felt that that was the best place to start researching improvements. After the implementation, you're right, it did improve it, but not to the point that we were able to justify all the complexity of a retractable step, because we need the step in the water. So ultimately, it was determined that was not enough of a contributor. I think there were other things that were not included in the predicted calculations, such as we're a flying boat. The predicted calculations do not accurately represent a flying boat fuselage. We also had engine nacelles. Engine nacelles were not accurately able to be included in those predicted calculations. So some of those discontinuities come from that discrepancy.
Very good. Also on your wind tunnel testing, I noticed that you didn't have any combined alpha and beta testing. Was there a reason for that? That is the angle of attack along with a yaw. There was no point, at least I didn't see any. Is that true? And if not, why didn't you include that?
That's an excellent question. I'll defer that question to Blake Bradford.
So for our wind tunnel testing, we wanted to isolate the changes just due to a change in angle of attack and a change in side slip. We did not want to see the combination of effects.
Okay. I'm going to pass this on so that other panelists can ask some questions.
First, I think I want to say I think it was an excellent presentation. Very well organized, very well presented. So this is the first time I've done this exact format, so forgive me here, but I'm not sure, there are just a couple questions. One is I'm not sure where all the requirements came from. So I got some of them were based on your research, including market research, that sort of thing. Were there specific requirements that were dictated from some entity, some particular company or otherwise?
Absolutely, sir. Actually, on the primary screen, you can see our RFP requirements, which is a request for proposal of a specific aircraft with these specifications.
Okay, I guess I missed that.
That's an appendice.
Okay. All right. It's probably good, I just recommendation to kind of, if you mention those up front, then it kind of sets the tone for, you know, what follows, how you met those. Let's see. Also, I guess I have a background in analysis, so I'm just curious about the structural analysis. Did you have specific safety factor requirements for the structural analysis?
Yes, that is correct.
Okay, and those were dictated by what set of requirements? Where did the requirements come from for safety factor?
I'll defer the question to our structural analysis, Blake Bradford.
So we decided to use so generally aerospace structures have a factor of safety of 1.5, and that's what we used for all lifting bodies, structures that we analyzed.
Okay. Great. One more question for analysis is, interesting that. So was there any need for any dynamic structural analysis, or was static sufficient, and if so, why?
Yes, we only did structural analysis. That dynamic analysis is beyond the scope of this course.
Okay. One other question about requirements. Was there any requirement that flowed down in terms of lifetime requirements? How long this vehicle needs to last?
We didn't have a specific RFP requirement on the life cycle of our specific aircraft, but that was included in our analysis of the life cycle cost of what the aircraft would be.
Okay. All right, thank you.
Thank you.
Yeah, I also want to say that it was a great presentation and liked it overall. When you were talking about your CL versus angle attack verification, there's a huge difference between your predicted value and what you guys had. Do you guys investigate that and try to figure out why?
Yes, absolutely. Actually, I'm going to defer the question to Chad Burge.
So during the preliminary design, we made the assumption, we tried to analyze what Reynolds number we were going to fly at, and we looked up the raw data plot, which is included in the appendice. And based off of that raw data, at the Reynolds number we were thinking was appropriate, we got a max CL of 1.6. It turns out that our Reynolds number was not, our initial Reynolds number assessment was not accurate, as we found out through wind tunnel testing. And that was a sharp discontinuity there. It turned out to be closer to standard reference.
Okay, yeah, that makes sense. I mean, I would just mention that in there, so otherwise it's not just a big question mark. So then later on when you're talking about your design changes, I thought it would have been cool if you actually picked up your model and just kind of referred to it. I mean, you should be proud of it, so, use it. And then on slide 42, you have the modified model at 10 degrees. It would have been cool to see a comparison with your A to B over there, so you could actually see what the design changes did. And then the only other question I had was, how you guys ended up with basically 700 extra hours of work. Because that's a big question once you get into the workforce. I mean, hours are everything, so how did that happen?
Absolutely. Actually, in an academic setting, we viewed our extra hours as a positive thing. The hours came from the extra commitment from our team to try and produce the absolute best model that we could in the time we had allotted. So the projected hour trend line was only calculating for 2 hours outside of class for every hour that was spent in class. And in reality, the compassion for this project from each team member drove us to actually want to produce the best model. And so that's where those extra hours came from.
Yeah, I mean, that makes sense. I wasn't in that too long ago, so I get it. It's just something to think about. So next time, you'd want to predict more hours, so then you don't go way over budget. So good job, guys.
Thank you.
Okay, I'd also like to say, good job. I really liked your flow visualization. You did a really good job with that. Let's see. On page 44, if I understood correctly, your initial analysis said your yaw stability did not meet the criteria. And then when you made the change from A to B model, it did meet that criteria. Could you further explain how the criteria was met, or what changed between A and B?
Absolutely. I can refer that question to Mark Van Bergen.
So for the yaw stability, we were actually stable in both configurations. The roll stability was the one that we were unstable in both configurations.
Okay, thanks for the clarification. Let's see. What happens when you add the props to stability and drag?
That's an excellent question. The props were not analyzed. We only analyzed the wind tunnel model and did not account for the thrust produced by the props.
What types of things would you think, what type of factors in your design would you think would be affected by the addition of the props into your analysis?
The addition of the props is going to cause a nose-down pitching moment, which is going to affect our static stability derivatives.
Okay, thank you. Page 29, this is your landing distance comparison on your B slide here. I noticed that your predicted values versus your landing distance column there, you met all the criteria. However, I noticed a difference of a factor of maybe 2 to 3 between your predicted and your, we'll call it your actual. What would you account as, for that difference in those values, 2 to 3x difference?
Absolutely, I can answer that for you. So our predicted calculations accounted for a CL of 1.61. In actuality, we were closer to 1.15 in our initial wind tunnel model testing. And the Brandt equation uses the coefficient of lift and coefficient of drag to calculate the landing distances. So that's where the sharp discrepancy in those landing distances came from.
Okay. Let's see. You added winglets to your model there, so you took the path of least resistance to reduce the drag. If you, for whatever reason, weren't able to add winglets, what other types of things might you change in the design to achieve a similar drag reduction?
We actually analyzed a few different methods before going with our winglets. One of them was blending the back of the cells to reduce the drag caused, as seen in the flow visualization throughout the presentation. Those had a significant drag contribution, and reducing those would have gave us a similar effect.
Okay. Question on page 56, your B slide. Your value coming out of your analysis came up with a 72 KSI, so which is less than the requirement. 76 out of 78 is less than 10%. So are you comfortable with that margin between the allowable and the actual value, or the analyzed value, being less than 10%? And if you're not, what would you do differently?
I am comfortable with that value being less than 10% because that is after a margin of safety of 1.5 was applied.
And my last comment is similar to Garrison here is maybe not a question but a comment of saying it's important to make sure that your estimate for the work requirements of the project are as accurate as possible. And you'll find that in a lot of cases there are overruns, but if you have line item funding from the government, let's say, and cost overruns they're frowned upon, then it's important to try to come in as close as possible and take that trip to Cabo that you ended up not taking for spring. So, great job on your presentation and on your project. Congratulations.
Thanks, sir.
Okay, good job, guys. And Kenny, how are you? You have a question, I'll bet.
Yes, sir.
Okay. I bet it's about structures too.
I can't jam them up too bad. Good job, guys. Going back to your CL curve, CL alpha curve, if you would. I don't have a booklet, so I'm just going off of memory here. You guys said you had a stall around 26 degrees alpha, or no? You said 10.
No, it was at 12 degrees was the onset of stall.
Okay, so you guys just kept going past that stall, or you attribute it to marginal, or? Because I'm still seeing lift throughout that wing. As you guys are increasing your alpha, you're still flying.
That's correct. I will defer that question to Mark Member.
A large component of why our wing stall is so docile, or while overall aircraft is so docile, while the wing does begin to stall at between 10 and 14 degrees, the sponsons actually didn't stall throughout the entire range from 0 to 26. And so the sponsons actually took over at high angles of attack and gave us quite a bit of lift in order to make our stall more docile.
Okay, so that makes sense. Second question, you guys on your sponson analysis, your structural analysis, you guys did use the dynamic load factor, but you guys never said what exactly that dynamic load factor was. So questions, I guess, are what was it and how was that driven?
I'll defer that to our structural analysis, Blake Brother.
So for dynamic loading, we used a CFR requirement for that. It would be an overestimate of what a normal landing was, and that value is 2.67 Gs. That would be over what a normal landing would be.
Okay, fair enough. When you mentioned it, you just said you used a dynamic load factor, but didn't say how it was derived, so I was kind of curious how that came to be. Overall, I would say good job, guys. I noticed there wasn't a lot of structural testing in this, but that's okay too.
Not as much as it used to be.
But again, good job, especially with the time constraints and the resources that you guys have available.
Thank you.
Thank you. Good to see you. Okay, I guess we could take maybe one question from the audience here. We got about 1 minute. Go ahead.
Yeah, so with your structural analysis, it looks like the aluminum properties you used were room temperature standard properties. Did you consider the properties of the operating extreme temperatures of your airframe?
The analysis was performed under ideal conditions because we didn't have time to perform analysis under different conditions, and that's a little out of the scope of the course.
Okay, well, with that small margin that you showed, are you concerned at all about maybe temperatures that are elevated temperatures and still maintaining your safety margin requirements?
I'll defer the question to Blake Bradford.
So this is a utility aircraft, and our maximum G loading is 3.13. We do not expect to be flying at that for normal altitude. So combining a factor of safety of 1.5 and almost an overestimate of the G loading Right now, the wing has 60,000 pounds put onto it, and our aircraft's weight's only 13,000 pounds. We are comfortable with the margin that it is at this moment.
Thank you.